Alright, in this lesson we're going to talk about related rate problems. They use derivatives and differentials to find related rates. So let's talk about why are they called related rates. Well, let's look at these squares. And if we look at the side length, we have a side length of 1, side length of 2, side length of 3, and the area is 1, the area is 4, and the area is 9. So we wouldn't say that the rate of change of area is equal to the rate of change of the side length. Over here, they're not equal. And if we look at this, if we double the side length, then we have 4 times the area. If we triple the side length, we have 9 times the area. So the area is related to the change in area is related to the change in the side length, but they're not equal. So that's why we call these related rates. Okay, and then we have some notation, a little different notation than we've been using. So up until today, we've been talking about the change with respect to x, and now we have x is no longer just a variable, it's a function of time, and if we differentiate with respect to time, then we would write the derivative like this. And up here, if we say that the area equals x squared, so x is the side length, area equals x squared, then the rate of change of the area is equal to the derivative of this. So if I say the derivative of a is dA dt, and the derivative of x squared is 2x, but x is not just a variable, it's a function of time, so we have to use the chain rule or implicit differentiation, and we'll say that the derivative of x is dx dt. So just like we have to do with implicit differentiation, when we have a variable, we'll multiply by its derivative. All right. So we have a square that's increasing. The side lengths are increasing at 2 feet per second. So we want to visualize that, and we just say that this is increasing 2 feet per second, and we would call the side length x, and that means this would be dx dt. and we'll have an organizer to put all this together, and it looks like this. So we have constant values that are given. Sometimes we have to find a constant value. We have rates that are given. We have rates that we want to find. So over here we label the variables. We have x is the side length, a is the area. And now let's look back up here. Side increasing 2 feet per second. Well, that's a rate, and we're going to call it dx dt. It's a given rate. Dx dt is 2 feet per second. Find the rate of change of area. Find the rate of change of area, dA dt, when the sides are 10 feet. That's when x equals 10. So now we need to know how x and a are related. We need an equation that has area equals x squared. There's a relation for a and x. We don't want this equation. We want the derivatives, or the derivative of this, dA dt, 2x dx dt. And then we substitute what we know and solve for what we're trying to find, dA dt. X is 10. Dx dt is 2, so we have 40, and that will be in square feet per second. And we can keep track of these units by looking at, this is feet, and this is feet per second. If you have feet times feet per second, we get square feet per second. Okay, pause the video and try that one. So now we have a square, and the area, the rate of change of area is 3. We have side length x. We need to find the rate of change of the side length, and we know that x is going to be 5. So we have a sketch. We start to organize some of the information, and then we'll organize it like this. Given, find, constant, rate, relation. All right, area increasing, and we have this rate here, so we know that's a given rate. dA dt is 3 square feet per second. Find the rate of change. Find rate of change of side length. Find dx dt when the sides x is 5. And then we have a relation for a and x. Area is x squared. dA dt is 2x dx dt. And then we just solve for whatever we're supposed to find, dx dt. dA dt is 3. X is 5, dx dt. We're going to solve for that. So we have 10, and we'll divide by 10. So 3/10 foot per second is the rate of change of the side length. The radius of a circle is increasing at 2 feet per second. So now we have a similar problem. We just will have a different relation between the two variables. So we have a circle and the radius is increasing. So we'd say dr dt is 2 feet per second. Find the rate of change of the area. We need to find dA dt when the radius is 6. So we have constant, rate, given, find. The constant that is given is a radius of 6 feet. The rate that is given is the dr dt, rate of change of radius, 2 feet per second. Find the rate of change of area, find dA dt, and we need a relation for r and a. Area of a circle is pi r squared. Then we'll do the derivative. dA dt is 2 pi r. Notice how the derivative of the area is the formula for circumference. So that's a nice connection to make. dr dt, the rate of change of r. We are trying to find dA dt, so that'll stay a variable, and we have r is 6. dr dt is 2. 4 times 6, 24 pi. And this is in its area, so that'll be square feet per second. All right, try that one, and remember that we're talking about volume. The volume of a sphere is 4/3 pi r cubed. Okay, pause the video and try that. So we have a sphere with a radius. The radius is increasing. dr dt is 0.5 meters per second. We want to know what's happening when the radius is 6, and we need to find dV dt. So we have given, find, constant, rate. The given constant is radius is 6. The given rate is dr dt. We need to find the rate of change of the volume, find dv dt. And we have a relation for r and v. V is 4/3 pi r cubed. And we need the derivative of that because we have to find dv dt. Dv dt multiplied by 3, and we get 4 pi r squared. And the derivative of the volume of a sphere is the surface area of the sphere. Solve for dv dt, 4 pi r squared dr dt, r 6, dr dt 0.5, and we get 72 pi. And this is volume in its meters, so it's meters cubed per second. Okay, so here we really need to draw a picture. And if we say the airport is there, an airplane is flying north. And there's maybe some more I should have explained in here, but we'll just say they both left from the airport. And one is flying north at 400 miles per hour. So if we say this is y, let's make that just a point. And the other is x. If it's flying east, then we know dx dt is the 600 and dy dt is 400. And we want to know the rate of change of the distance between them. So how fast is this distance changing? And we'll call that s. We can't call it d because with derivatives it doesn't work out well if you say dd. All right, x, we want to know when x is 8 and y is 6. Let's organize this information. We have constant, rate, given, find. Okay, constants that are given. Y equals 6, x equals 8. Rates that are given, dy dt is 400, dx dt is 600. And what rate are we supposed to find? The rate of change of the distance between them, ds dt. We need a relation for s, x, and y. Since it's flying north and east, they are flying north and east, then it makes a right triangle, so now we can use the Pythagorean theorem to relate them. X squared plus y squared equals s squared. We do the derivative, 2x dx dt, 2y dy dt, 2s ds dt. And we'll substitute, we need to find ds dt, so we'll substitute for x. We have an x, we have a dx dt. Dy dt, we have a number for that. Y, we have a number for that. S, we don't have a number for s, so that could be something we could put in here and say it's a constant that we're supposed to find before we can continue, so we can do that with the Pythagorean theorem. And we have 6 squared plus 8 squared equals s, square root of that. So that's going to be 10 equals s. Now we have a number for s. 2 x dx dt, 2 y dy dt, 2 s ds dt. So this should be 9600, 4800, 20 ds dt. And we'll end up with 720 miles per hour is ds dt. That's the rate of change of the distance between the planes. And we'll stop there.